So let's talk about a huge challenge in the world of AI. Imagine you have one model that's an absolute genius at writing code, and another one that's a master of mathematical reasoning. How do you combine them into a single multi-talented supermodel? Well, we're diving into a breakthrough research paper on a technique called SimMerge, and it offers a surprisingly smart answer to that very question. So how did we get here? And more importantly, where is this new technique going to take us? We'll start by looking at the boom in all these specialized AIs and the massive bottleneck that it's created. Then we'll introduce SimMerge as the solution, pop the hood to see how it works, check out the pretty impressive results, and finally we'll connect it all back to the new economics of AI. All right, so first things first, let's set the stage. We are living through an absolute explosion of AI specialization. The whole idea of a single giant AI trying to do everything, that's kind of giving way to a world of finely tuned expert models. What's happening is that thousands of these fine-tuned models, or checkpoints, are popping up everywhere. You can think of each one as its own little expert brain, trained on very specific data to get incredibly good at just one thing, whether that's understanding legal docs, cranking out Python code, or handling complex customer service chats. So you end up with this vast library of amazing skills. We have all this power, but it's siloed, It's all locked away in its own little box. The real challenge for companies and researchers isn't just about creating more of these specialists anymore, it's about figuring out how to make them work together to create something even more powerful. And that brings us right to the heart of the problem. This major roadblock that this new research is trying to completely demolish. It's what the paper calls the Great Merge bottleneck. This really is the million-dollar question, isn't it? You've got all these expert models. You want to merge their skills. But how in the world do you actually do it? Turns out the traditional ways have some really serious problems. The old way is basically just brute force. It's called merge and evaluate. You take two models, pick a merging technique, kind of smash them together, and then run a whole battery of tests to see if the new combined model is any good. And if it's not, well, you try again with a different technique or a different order and hope for the best. And this whole approach is just fundamentally broken. Why? For three really simple reasons. It is slow, because every single one of those evaluations takes time. It is expensive, because each one of those cycles burns a massive amount of computation. And most importantly, it's completely unscalable. The number of possible combinations just grows exponential. And hey, don't just take my word for it. The researchers themselves put it perfectly in the paper. Trying every single combination to find the best one is, for all practical purposes, impossible at scale. You just can't afford the time or the money to test every single possibility. This is the bottleneck. But this is where our hero, SimMerge, enters the story. It offers a totally different way of thinking. Instead of guessing and checking, it predicts the perfect mix before you even start any of the heavy lifting. This really just frames the massive shift in thinking here. The old way was this blind, costly cycle of trial and error. SimMerge, on the other hand, introduces an intelligent, predictive method. It does all the smart work up front to avoid all that expensive guesswork later on. Now, let's be super clear about something. SimMerge isn't inventing some new kind of superglue to stick models together. It actually works with the methods that are already out there. You might have heard of them, like linear, SLERP, or ties. The real innovation here is that it acts as a lightweight trained selector. It's like a matchmaker for AI models, not a new recipe for merging them. Okay, so let's pop the hood and see how this prediction engine actually works. I mean, how can it possibly know the best way to merge two models without, actually merging them first? This diagram here lays out the entire framework. It all kicks off on the left with the inputs, the two specialized models you want to merge. From there, it moves into the real magic of the process, computing similarity. Those similarity scores then get fed into the predictive selector, which makes the call. And then finally, the merge executor performs that one single optimized merge to create your final model. So how does it compute that similarity? It uses a handful of really clever and, more importantly, inexpensive signals. Think of it like trying to figure out if two musicians will play well together. You could look at it from a functional perspective. Do they play the same style of music? That's kind of what something like Kale divergence does. Or you could look at it structurally. Do they use the same type of instrument and tuning? That's more like what weight cosine similarity does, which compares the internal architecture, the guts of the models. The entire process really just boils down to these three super efficient steps. Step 1, compute those cheap similarity signals. Step 2, based on those signals, predict the optimal merge strategy. And step 3, just do it. Execute that one strategy. Notice what's missing? There's no loop, no going back to the start. It completely eliminates the entire evaluate part of the old merge and evaluate cycle. Of course, this all sounds great in theory, but it's only useful if it actually holds up in practice. Can a predictive model really outperform the old brute force method? Well, the researchers put it to the test. And wow, the results are incredibly compelling. See all these different colored bars? Each one represents a different merge method, but that green bar, that's SimMerge, and look at it. Across 4 different domains, code, math, multilingual, and RAG, SimMerge consistently delivers the best performance. It adapts where the fixed one-size-fits-all methods just can't keep up. So let's put a hard number on it. Success is measured by how much of an expert's original skill is kept after the merge. On average, SimMerge closed an impressive 65% of that performance gap. Now, to really understand just how significant that is, we need some context. Well, consider this. The absolute best you could do by just picking one of the old methods and sticking with it was closing only about 42% of the gap. That means SimMerge's predictive approach isn't just a small improvement, it's a massive leap in performance and reliability. And maybe one of the most exciting implications here is just how well it scales. The selector model was trained on merging 7 billion parameter models, but then they were able to use it to make effective choices for merging these gigantic 111 billion parameter models with no retraining at all. This proves the approach is robust and totally ready for real-world, large-scale applications. So let's zoom out from the technical details for a second and talk about the business implications. What does a breakthrough like this actually mean for the companies out there building and deploying AI? The impact is huge. By cutting out all the guesswork, development cycles get dramatically faster, which leads directly to massive cost savings on compute power. But it's about more than just saving money. It enables something much more profound. Teams can create more capable, versatile AI by combining the assets they already have, instead of training brand new ones from scratch. And importantly, this isn't a static solution. The research even proposes a version that can learn and adapt as the whole AI ecosystem evolves. Ultimately, this represents a fundamental shift in the economics of AI development. For years, creating top-tier, multifaceted AI has been a game played only by organizations with nearly unlimited budgets. SimMerge helps to change that. So the question it leaves us with is this: if you can finally build a supermodel without super costs, what becomes possible?